Alright, so we do have some new vocab just to reiterate the things that we've been talking about. So, a differential equation, by definition, is an equation involving a derivative. So a differential equation is an equation involving a derivative. We order differentials the same way we used to order equations in algebra. Standard form says highest to lowest. It's just you. Where do you see involving? It's involved. Up there.
Involved. I don't know.
Oh, no. The L should be before the B.
Yeah, I was going to say it just looks funky.
I thought you were trying to say that should be the word involving. And I was like, no, involved is right.
I spelled it right without even thinking about it.
I spelled it wrong.
You're going to give me a little bit.
Everyone I first told me I was wrong and I got scared.
Did anybody here recently take the new SAT test?
No.
I heard it was easier.
You're going to copy down the wrong letters.
Well, I did copy down the right wrong letters.
Ew.
I remember when Brandon drove 120 miles per hour in the SAT test.
We need to put the part in parentheses.
This is really working.
The parentheses, you don't have to read them. They're just a side thought.
Okay, a side note. Cool.
So it's just like addition, subtraction, multiplication, division, derivatives, antiderivatives.
Alright. The second word. A definite integral has limits of integration. A definite integral will have limits of integration.
Wait, you used to have limits of
These are just like making sure you know the difference in terms. An indefinite integral is the set of all antiderivatives of a function with respect to x and is denoted by the integral of f of x dx. We know that all antiderivatives differ by a constant, so that the derivative of capital F prime of x equals f of x, thus giving the integral of f of x equaling capital F of x plus c, where c allows this to be a family.
Alright. Tis or skill. There's no
We
other
work
word.
around this.
Why don't you try it?
There's purple ones.
I don't know for purple.
Okay.
I've learned to just aim at the back of the wall. If you try to aim at it, you're always in the
So, essentially what we're doing today is a mixture of integration and derivatives again. But we're going to do separation. So yesterday we talked about u, du, and we had the dx on the other side, and we substituted. So today we're going to use that same idea, but now we have to separate the variables into parts. So just to reiterate, we have our rules once again. Power rule says you add 1, divide by your new power. The rule for 1 over x tells us it's ln x. E to the x is e to the x. And then if it has a constant with it, it's e to the kx all over k. Same with all the trig functions. And then these ones, we haven't hit on them too much. We're going to see them a little bit in here. The two inverse trig functions that are commonly seen are inverse tan and inverse sine. So inverse tan looks like 1 over x squared plus 1, and inverse sine looks like the square root of 1 minus x squared. And then we have our a to the u, so it's a to the u over ln a. Everybody pretty good with our formulas? Okay, so let's evaluate some integrals. So example number 1, you have the integral of x to the negative 3 plus the cube root of x minus 1 plus e to the 3x.
I think that may be the ugliest thing we can think of.
Oh, I'm going to make that way grosser.
Yeah, you definitely keep going with science, but science games, just turning things up.
And you can put coefficients on this. Those x's are pretty basic.
Put coefficients on the side that include science.
Yeah. Okay, so this becomes x to the negative 2 all over negative 2. That's our power rule. The cube root is like x to the 1/3. So if you add 1 to 1/3, you get x to the 4/3 over 4/3. A constant gets a variable. And yesterday we did the e's, so e to the 3x would get a
1 over 3.
Good. And what do I need at the end of this? Okay. We don't like negative exponents, so we'll clean this up. It's negative 1 over 2x squared plus 3 over 4 x to the 4/3 minus x plus 1/3 e to the 3x plus c. Okay, so we almost went to separate this in a way, because what's happening here? We have a term that's derivative isn't just 1, so we need like a u sub for that part, and we can take out the constant of the other part. So I almost want to treat this like two separate integrals. It's the integral of 3 sine x dx minus the integral of sine 3x dx, where we take the second integral and we kind of say, all right, u is 3x, du is 3 dx. So what am I going to have to add back to my answer? Well, it's missing a 1/3. So you get 3. Antiderivative of sine becomes negative cosine. Good. Minus, there's my 1/3. And again, it's like negative cosine u, but we know u is 3x. Let's see. We had to adjust for the 1/3. So it's kind of like 1/3 integral sine u du. But sine isn't very complicated, so we kind of just say, okay, I have to account for the 1/3.
So anytime you have a leading coefficient, you have to split it into multiple numbers.
Yes. Or at least adjust for, it's not necessarily the leading coefficient, it's the coefficient inside the angle and the sine that made me split. So you get negative 3 cosine x plus 1/3 cosine 3x plus c. Okay, example 2 changes our wording a little bit. So again, these words are evaluate each integral. These are indefinite because they have no bounds. They get the c's and the constants. We also have wording that says find all functions y that satisfy dy dx equals secant squared x plus 2x plus c. So this is kind of like what rule from chapter 5?
The one where you derive it and you fold it or whatever and you get the same thing.
So yeah, this is kind of like an FTC, right? So we're given it a derivative and we want to find its antiderivative. So, in order to take an integral, what do you have to have? What's that called in the integral? Think back to this example. What did I have here? What's that dx called?
Variable
Yeah.
integration.
Yeah, it's the variable of integration. It represents the variable with which we are integrating with respect to. So what we have to do is this dx needs to move or transition to the other side of the problem. Now, in order to find y, the derivative of y became dy. So to find y, we're going to integrate the left side, but it's like algebra. If we integrate the left, we have to integrate the so the integral of 1 dy becomes y. And now we just kind of take antiderivatives of the right side the same way we know. The antiderivative of secant squared becomes tangent. Antiderivative of 2x becomes, and the antiderivative of 5 plus the constant of integration, c. That's it. So solving differential differential equations involves finding a unique equation that satisfies some initial condition. The order of a differential equation is the order of the highest derivative involved. A unique equation occurs by solving for C, given that f of A equals B, where A and B are real numbers. Holy moly, lots to go on. But essentially what that's saying is, okay, we're still going to antiderive, but now the initial condition problems are going to look a little bit different. So we're going to go backwards and kind of find C again. It's just a different setup of C. Okay? So it says solve the initial value problem explicitly, aka we need to separate our variables. So, we are given dy dx equals sine x when y of 0 equals 2. So in order to find y, we have to separate our variables. Integrate both sides. So you get y equals negative cosine x plus c. What?
U2 equals negative cosine of 0 and then plus. Oh, wait, never mind.
I was like, what? Okay, so then we use our initial condition. So the initial condition says, all right, y of 0 equals 2. So that's like saying 2 equals negative cosine 0 plus c. What is the cosine 0? What is the cosine of 0? 1. So you get 2 equals negative 1 plus c. So add it over. So c must equal. So the equation that satisfies this initial condition is y equals negative cosine x plus 3. So that is the equation that satisfies the initial condition. Okay? Again, we have a little bit of a mix-up now. Now it's dx dt equals 1 over t minus 1 over t squared plus 6 given x equals 0 when t equals 1. So how do I separate and solve?
3 is on the entire right side and multiply it by dt and then integrate both sides.
Yep, so we'll move over that dt and then we'll integrate. So the integral of 1 dx becomes x. T to the negative 1 or 1 over t is ln t, good. And t has to be inside absolute values because we don't know the value of t yet. T to the negative 2 will become what?
Positive 1 over t.
Good. So it becomes positive because you add 1, so you get like t to the negative 1 over negative 1. Double negatives make it positive. And then the 6 will get our, and then c. Good. Plugging in those initial conditions. X is 0. And t is 1. So natural log of 1 is? Okay. So 1 plus 6 is? So C must equal? ln E is 1. Yep. So you get x equals ln absolute value t plus 1 over t plus 6t plus -7. That is initial conditions and separation of variables. Okay? Let's look at what happens if you have discontinuity inside there. No. So again, go ahead and read through that example at the top. Okay, so it says find the particular solution to the equation dy dx equals 2x minus secant squared x, whose graph passes through that point. So what do we know about secant squared? When does secant not exist?
Whenever sine is 0.
Yep, so pi halves and negative pi halves or 3 pi halves. So if we're talking about the point 0, 3, is that going to be a point of concern? Yeah. So again, 0, 3 is in that interval. We can find the solution only on a particular interval then. So we can only find solutions So our solution will only be true from negative pi halves to pi, because we know secant has repetitive asymptotes between them. We can only look at the asymptote from here to here. We can't really compare anything around it elsewise. So, first thing we want to do is what we've been doing. What are we going to do to our variables? Yeah, separate them. You can write them in either order. I just started to put a negative. Okay? Antiderivative of secant squared is tan. The negative doesn't affect that. Yep, it's just a negative tangent. 2x is x squared, and then we have our c. Plug in your points, so we know that we're talking about 0, 3. So we get 3 equals negative tan 0 plus 0 squared plus c. We'll put tangent at 0.
Wait a minute. 5 0.
0. So the negative 0 doesn't matter. 0, 0. C must equal
3.
We actually looked at something similar to this when we talked about FTC, and we talked about the 0 to 8 bound, and then we made it 8 to 8 so we could have continuity. And we're going to almost go back to that again. So we have initial value problem du dx equals the square root of 2 plus cosine x, when x equals 0 and u equals negative 3. Yeah.
Because secant is cyclic, repetitive, can we then use this for the rest of the intervals between the discontinuities?
The 0, 3 point will change, though. Like, the initial condition wouldn't be true, because, like, 0, 3 would not exist from pi halves to 3 pi halves.
So it's
That's
only
why
where the
it's
initial
just-
condition exists?
Yes.
Like the bounds of the...
And that's why I even picked that interval versus this interval. Because 0, 3 is going to live between negative pi halves and pi, because 0 lives in here. So that's why it's like kind of talking about the closed domain. Does that make sense?
Yeah.
Okay, FTC, remember, fundamental theorem of calculus says that you can have an input and an output, and you can take a derivative of an integral, and you end up just kind of getting a manipulated integral. So what we want to do is we want to set this up so it looks like FTC. So what do we know the first things we're going to do is to make it look like FTC? We got to do what to the variables? Yeah. What do I get? du on one side and dx on the other. And then we're going to integrate. So essentially what this is saying is, how could I integrate this with bounds to make it look like FTC? What would go where if I wanted to integrate this with bounds? So you can set this up using fundamental theorem of calculus and your initial conditions to get the same answer we would get if we took the integral this way. So let's say we didn't know, what do we actually need to do this problem, and what can't we use because we're missing something.
Can you break it down to like u equals 2 plus cosine x?
But if we do that and we make u equal 2 plus cosine x, what's du going to be?
Negative sine x.
Do I have a sign? No. So that's what I'm saying. Like, we have to now apply FTC in a way that all we can do is really set up our thing. So it says your answer will contain an interval. So how could I set up the bounds? Go back to FTC. How could you set up the bounds so you can have your initial condition? You know a condition. Think about when we had area under the curve. And let's say I told you the area of this is 3 and the area of this is negative 6. What's the value at this point here? 9. Yeah, it's negative 3.
The
Because
library
what
will
did
be
you
closed
do? Added
3. Please do not
the areas
send students
together.
to the library.
So let's take that idea of adding the areas together to create an integral. We are given, in this case, at 0, the area is like -3. So it's kind of like saying, ooh, when I started this point, the area over here was -3. So it's kind of like saying at 0, we're at -3. If I want to define the area over here to some point x, what would your integral start with and what would it end with? Okay, so now I want to take 0 to x of what I have. How does that 3 come into play? What would I do with that 3? How could I incorporate the 3? Because it's, or -3 rather. It obviously has meaning. What did we do when we added up the two areas before? First one plus the second one. So if this is kind of like the second one, what did we need to do with the first one? Add it, subtract it in this case because it's negative, but we need to incorporate it. So it's like initial condition plus the new area will equal u. Initial condition plus the new area will equal u. I know. But this is kind of leading into where we're going to go on Monday.
Oh, jeez.
We're going to talk about inputs, outputs, slip fields, and families of functions. Yes?
Will the upper bound always be maxes
In this case, because if, let's say it said, solve the initial condition, the initial value problem when x equals 0 and x equals 0, and we know u equals -3, and then it could say for x2 equals 5. And then that would be 5. Like, and then you could actually find it. But this is just saying, solve that value problem so that it's set up and we have kind of some ambiguous value. Okay, homework is in our book.